Hi, AP Chem students. This is the class video for Monday, November 23rd, 2020. So our agenda for today was to go over the 3.11 to 3.12 problems. We did a little practice balancing. We reviewed types of reactions and classifying those reactions, and very quick one problem at the end on net ionic equations. So this video will include a few more examples of net ionic equations. And then there was a survey and a conference for Q1. We also talked about our favorite Thanksgiving foods. So homework was to take notes on AP Classroom for videos 4.1 to 4.5, and you'll submit your notes by December 6th, and then complete the practice problems on net ionic equations, which are due by December 6th. Answers will be there for posted at some point next week for you to check in advance so that we can spend more class time going over the things that you really need to understand and have questions on. Okay, so the other reminder was that Zoom is only going to be accessible by K-12 accounts after Thanksgiving break. So make sure you use your K-12 account to join Zoom. So these are the 3.11 to 3.12 practice problems. This one was gone over in the last class video, but here's the solution here. Feel free to pause and check your answer. The next problem is about using the spectrophotometry, but this is all kind of text that is unnecessary for you to actually answer the question which is being asked, which is the energy of one photon. Remember that in this equation, E equals h nu, that is the energy of one photon of this frequency. Here's the answer, the solution and answer. Feel free to pause to check your answer and make any corrections. For number 3, here's our old buddy PES spectroscopy. And remember that energies go from high to low. So the valence shell is this peak on the very right, the rightmost peak. And so that's the energy of the electron, the binding energy of the valence electron there. So that energy is right here. And then we can solve for the frequency using our E equals h nu, but the question asks for the wavelength. So using our wave equation, our light wave equation, we can solve for the wavelength, plug those numbers in, and we get 203 nanometers. Just as a reminder, 1 times 10 to the 9 nanometers is equal to 1 meter, and you should memorize this because it is not on your equation sheet. These other equations are, but you need to memorize some conversions. I would write this on your equation sheet if you can. All right, the next one has to do with ozone and basically what sort of photons can break the ozone, the oxygen-oxygen bond in ozone. And we can solve for first the energy of the photon using E equals h nu and the frequency. Then using that frequency and energy of that photon, we can figure out how many kilojoules per mole that is and compare to the amount of energy needed to break the bond in ozone. So we can see that 399 kilojoules per mole is greater than 387. So yes, this photon, if it hits a single a single ozone molecule, will break a oxygen-oxygen bond in ozone. Then finally, the last one, again, is very similar. We are going to solve for the wavelength of this photon and figure out what color the photon that light is based on the wavelength that we find. So we can see here that here I've just decided to use my E equals h nu and substitute in for my frequency. So when I substitute in, I end up with E equals hc over lambda. I'm going to solve for lambda by cross multiplying and then plug in my numbers. I get a 600 nanometer photon, which is an orange photon. The color of the photon is orange. Then we went and over a few of these balancing chemical reactions, which hopefully should be mostly a review, but if not, there's a couple videos that I posted right here on the worksheet that you can watch to help you remember how to balance equations. So I will scroll through this and you should check your answers. We also talked a tiny bit about the types of reactions, and I've labeled a couple of these. For example, one is a synthesis because we have two substances coming together into one product. So that's the defining characteristic of a synthesis reaction, one product. Here, a decomp has one reactant. Okay, so one reactant breaking up into two or more substances will be a decomposition. Single replacement, if you see elements, a single element and a compound, and that single element replaces an element in the compound and pushes out another single element, this is called a single replacement. Here in 5 and 6 are double replacements or metathesis reactions, where we have two compounds and ions switch places. So you can see here in number 5, this hydrogen, H plus ion, hydrogen ion, combines with the OH to form H2O, and then the Pb plus 2 ion is combining with the Cl minus ion to form PbCl2. So these are the double replacements where ions switch places. Same with number 6. Combustions are pretty easy to recognize because we have a product of CO2 and H2O. Also, we have oxygen being combined with a hydrocarbon or some sort of carbon, hydrogen, oxygen, some organic molecule right here. I'll scroll this down, and these are the solutions to the number 10 through 18. So these two reactions, 17 and 18, produce carbonic acid, which is down here. And carbonic acid decomposes readily into water, H2O, and CO2 gas. So this is the acid that's in soda. We inject a bunch of carbon dioxide into water to make seltzer, and then we seal the can. So it's under pressure, the can's under pressure, and then when we open the can, CO2 starts bubbling out. That's all our CO2 bubbles coming out, and our carbonic acid continues to decompose into H2O and CO2, which is why your soda tastes really flat after the carbonic acid has decomposed, and also your soda tastes flavorless, doesn't have that acidity anymore. Okay. So after going over the worksheet, we went on to talk about Unit 4. Unit 4 is on chemical reactions. So here are the objectives for Unit 4. You should be able to identify the difference between physical changes and chemical changes, both symbolically, both using particle models as well as just the descriptions of what happens in an experiment or happens in the lab. You should also be able to balance a chemical equation, classify the type of reaction, draw a particle model for chemical reactions. We'll do a lot of this when we get back. Identify signs, physical signs that a chemical reaction has occurred. predict the products for double replacements, and then identify spectator ions and write net ionic equations. This is a big one, okay, that we're going to focus on in this unit. And then finally, once we get through these objectives, we'll be applying what we know about reactions and using them to do stoichiometry. All right, so what's this called? This is a chemical equation. So here's our symbolic representation. Here's a particle model of this equation. As a reminder, these things on the left are called reactants. The things on the right are called products. This arrow in the middle is called the yield arrow. It also can stand for producing things or equaling things. So we could say that 2H2 plus oxygen yield 2 H2O molecules, or produces or equals 2 H2O. Which of these is a physical change? This is a physical change. You can see here that the reactant H2O is in a liquid state, but on the right-hand side, we have H2O again in the gas state. The substance is still the same chemically. No bonds have been broken except for our IMFs, right? Our IMFs have been broken to change H2O liquid into a gas. There has been a change of state, but this is just a physical change. The one on the top here is a chemical change or a chemical reaction. Now, I'm often going to abbreviate reaction as RXN, meaning reaction. So this is an actual reaction. We have bonds breaking. Atoms are rearranged to form this new substance right here. This is new. Okay, so that's a new substance that is formed through the chemical change, whereas a physical change, we still have the same exact chemical species before and after, but a physical property of that substance has changed. So the reason why we balance chemical equations is because of this law of conservation of mass and energy. Okay, energy is part of this, but we have to have the mass of the reactants equal the mass of the products. We can't destroy or create new mass, so that law has to hold true. Oh, going back here, just keep in mind here, if the reactants weigh this much, right, our products have to weigh the same. This law, the law of definite proportions, requires that chemical substances have a specific formula. You cannot change the formula for NO2, for example. NO2 is always NO2. There's always one nitrogen for every 2 oxygens. Same with N2O. We have 2 nitrogens to 1 oxygen. These formulas are fixed. It means that if we know how many atoms of nitrogen to how many oxygens there are, if we know that ratio, we know the formula and we know the substance. And the substance will not change. Its proportion of its elements, fixed in place. And just a reminder, right, we have our 7 diatomic elements. Here's H2 and O2, and here's our other 7 diatomics. There are a couple other elements on the periodic table with some different forms, but we won't really need those. They will be given to us in most cases, but sulfur and phosphorus are a little bit unusual in that respect. All right, so then we started a pair deck. Here's our 5 types of reactions from Chem 1, these synthesis, decomposition, single replacement, double replacement, and combustion. Now, in this unit, we're going to be also classifying things a different way, which we will talk about. We will also classify things as acid, base reactions. We will also look at redox reactions. These are reduction oxidation reactions. So those are two things that will come up. We'll look at special decompositions. Okay, so some special decompositions, we'll be able to look at those. So these are not the only ways to classify the types of reactions. Okay, there are many other ways to classify reactions, so we'll learn about those in this unit as well. So our first Pear Deck question was, what are some common signs that a chemical reaction has occurred? Well, here we go. Here is a precipitate. A precipitate is just a solid substance, okay, that is created through a reaction. So you can have a precipitate forming. Along with that, you might see a color change. Here we see fire, right? Fire is an indication that some chemical reaction has happened. Light being given off. In class, I burned magnesium, and magnesium gives off a intense bright light. Here we have chalk being placed into hydrochloric acid. We see a gas, okay, bubbles. This is a sign that something new has been formed, okay. Other indications could be a smell from a chemical being formed and given off, and we smell it. So those are some general common signs of a chemical reaction. The other thing going along with fire and light is changes in temperature. So our exothermic versus endothermic reactions. All right, balance this equation. Here we go. We'll put a 2 here, put a 2 here, and then our oxygens are balanced, our nitrogens are balanced. This is nitric oxide. It's this beautiful brown gas, but very poisonous. Is this equation balanced? Well, let's see. Here we have carbon equals 1, H equals 4, Cl equals 8 here. Okay, because I got 4 times 2. I'm going to check the product side. C equals 1, H equals 4. Okay, and Cl, there's 4 here plus 4 over here. That's a total of 8. Yes, this equation is balanced. All right, this balancing equation. Okay, so here we have HCl. Let's see if we can balance this up. I could put a 3 here, but I see that I have a 2 over here. So let me try instead putting a 2 here. Then I'll need 2 Fe's. I have 6 Cl's. So I want a 6 here and a 3 here. Okay, what type of reaction is this? This is a single replacement. We have a single element going in and kicking out, okay, or replaces hydrogen. Iron replaces hydrogen here. So, and then hydrogen is by itself. Reminders, this S in parentheses means solid. Aqueous, AQ, means dissolved in water. Okay. L in parentheses is liquid, and G is gas. All right, Fred and Wilma. Betty takes over Wilma's place. This is single replacement. Now Wilma is by herself. Here we have A and B coming together into an AB molecule. This is a synthesis, and same with the red circle and blue square. Oh, wow, I'm dating myself here. This is definitely old news here, but here we have double replacement. People are switching partners. Okay, so Na was with Cl and K was with Br. Now Na combines with Br, okay, and Cl combines with K. And then we have KCl and we have NABR. Here we have AB, and AB splits apart into A plus B. This is a decomposition. Here, yeah, you probably recognize this immediately with the H2O and CO2, and as well as the oxygen that's burning the fuel. These are combustions. Now we're looking at a particle model. So if we take a look here, we have one compound here. This is one compound. And it's breaking up into one compound and an element, one element. Okay, this is a decomposition. Right? We have one thing breaking up into two pieces. Another particle model. So we have one compound in our reactants, a compound and one element. And we are getting in the products a element, right? These are the same atoms, so that's an element right there, plus one compound. And we can see that this green element has replaced the gray element here and kicked it out. So this is a single replacement. Here, these are all combustions. These are not balanced. Here, we want to balance this combustion reaction. So again, always balance the carbon and hydrogen first when we're doing combustions. So we want to put a 2 here to balance the C. There's 6 H's on the left. I want to put a 3 here to make this be 6. Now I'm going to add up the oxygens on the right. That's 4 oxygens plus 3 oxygen. That gives me a total of 7 oxygens. So I could put a 7 halves right there, because 7 halves times 2 gives me 7 oxygens, and that would give me the correct number of oxygens. But what I could do to make this look a little nicer is multiply all my coefficients by 2. Okay, then I'll get rid of this fraction and I will have 2C2H6 plus 7O2 yields 4CO2 plus 6H2O. So I multiplied those out and I've gotten rid of that fraction. What type of reaction is this? We've got 2 reactants and we make 1 product. They combine. This is a synthesis. If we had to draw a particle model of this reaction, we would need to draw 4 P's. First, we want to make a key. Okay, so I'm going to use for my P, I'm going to use black. So I'm going to say P is a black circle. Oxygen is usually red, so I'm going to use oxygen is a red circle. Okay, so first for my phosphorus, I want to draw a box for my reactants. Okay, I'm going to label this as reactants. And I'm going to draw one. And it doesn't really say what state of matter they are. Let's just make them all gas. So 1, 2, 3, 4, because there are 4 P's. Now I need to make 5 O2 molecules. So here's 1, 2, 3, 4, 5. Okay, so there's my reactants there. Now I want to draw my products. I'll draw another box for that. And we will spend time drawing these diagrams. So I need 1 molecule of P4O10. So I want to draw, and the connections, not really important. Okay. The actual Lewis dot structure, I'm not sure how that looks. But we want to have the correct number of each element. We also want to make sure that we're showing a molecule with them all connected together. So what is that? 1, 2, 3, 4, 5, 6, 7. Let's put 8 here, 9, and 10. So we want to make sure that this is a single molecule that we're showing, because this is one molecule right here. All right, so now we want to guess what type of reaction this is based on just the reactant. So here I have an ionic compound. Let's go back to, here we go. And make that a little, go back to that. Make sure I got the right thickness. Okay, so we want to look at the reactants here. We have an ionic compound, right? Metal and nonmetal. We have 2 ionic compounds. Both of these are ionic compounds. And they're both aqueous. We'll talk about solubility a little bit in a moment right here. And we want to figure out what sort of reaction this is. Well, if we have 2 ionic compounds and we see a precipitate forming, this is a double replacement. Okay. So then we want to actually write the products. So for a double replacement, remember, we want to we want to switch the places of these positive ions. Now, it might help you to put in the charges of each of these ions. So here, when I take my K, I'm going to combine it with my NO3. I will get KNO3, and then I will combine my PB with the I, okay, and I will get PB, remember it's +2, so I need 2 I- ions, and I'll get that, okay, and then I have to balance. So I have 2 NO3s here, so I need a 2, and a 2, and this is now balanced. How do we know that a chemical reaction has occurred? Well, if you take a look at this solid here that's forming, this is a precipitate. And in the lab, if you perform this reaction, you would see this bright yellow precipitate that forms. So when you see a precipitate forming, when you see this formation of a solid compound and we'll talk about how we know that this is solid in a moment, right? We know that a chemical reaction has occurred from that sign. Now, how do we know this is solid? Well, in AP Chem, there are a few solubility rules that you need to memorize. So you would need to memorize that group 1 and NH4 plus are soluble, meaning aqueous. So if you see any compound that has group 1 cations, okay, or ammonium cation, these are soluble. They will form aqueous solutions. So that's one rule you need to memorize. And then the second is that nitrates are soluble. And there are other rules as well, and you'll use them on your homework worksheet. But for AP Chem, these are the ones you need to know, need to memorize them. Okay? So you got to memorize those 2 solubility rules. All right, so that's why you can see this K plus is group 1. That's aqueous. That's soluble. This is nitrate right here. I should probably write that. NO3 minus is nitrate. That's soluble. That's why this is aqueous. This is aqueous because it's got K plus and nitrate. This is not soluble based on the solubility rules that you'll see on your worksheet. All right, so if we want to draw a particle model for this reaction, what do we have to do? Here, I'll draw the reactants in this beaker over here. Imagine it's filled with water. Maybe I should use blue since we typically think of water as blue. I'm not sure why, but it's not always blue. It's colorless. So here we want to draw 2 Ki. Okay, so 2 formula units of Ki. These are ions, remember? So I'm going to draw this as a K plus and a K plus. I also have 2 I minuses. So let me draw that as I minus, and these are floating around in solution. There's ion dipole forces around them. Okay, here we have 1 formula unit of PbNO3, so I need a Pb2 plus ion and 2 NO3 minus ions. All right, so that's our particle model of the reactants. Over here, now we let them react and they form a precipitate. This stuff at the bottom, PbI2, is stuck together on the bottom like this. It's that precipitate that's sitting there, that yellow stuff. But these ions right here, the K plus, are still aqueous. They're just floating around. Got 2 K pluses and 2 NO3 minuses. They're freely floating. Okay, and that's what we would see in the products. All right, so we're going to break up this equation into a complete ionic reaction. Here's where we're getting prepared to do our net ionic. So steps: break up all aqueous ionic compounds. Keep together. Keep together. Solids, liquids, and gases. Keep those together. Don't break them apart. Okay, so break up all aqueous ionic compounds into their ions. Because, you know, these are dissolved in solution. They're just freely floating around. So let's see what this looks like on the next slide. So here's our complete ionic equation here. 2K plus, 2I minus. You can see I've broken up all of the aqueous substances into there, and this should be aqueous. Okay, that should be aqueous. I don't know why that disappeared there. But the solid we keep together. So what are the spectator ions? These are the ions that appear left. Oh, let's call that appear as a reactant and product. No changes occur to them. Okay, so these are ions that do not change over the course of the reaction. They're just floating around and doing their own thing. If you look at the complete ionic, we can see that we have 2K plus here on the left and 2K plus on the right. And there's a reason why these are called chemical equations. They're just like algebra. So if you see the same thing on the left and the right, we can cancel this out. That is a spectator. Spectator ion. Just watching the whole thing. Let's see, is there another ion that appears on the left and the right? Here we go. 2NO3 minus. That we can cancel out as well. This is another spectator ion. All right, so we've got those 2K plus and NO3 minus are the spectator ions. So when we cancel the spectator ions here, K plus, getting rid of K plus, getting rid of, okay. It's not that they're not there. Be careful with this. Just because we're canceling them in this complete ionic reaction does not mean that they disappear. It's just that they're not participating in the overall reaction, right? So what we want to do is write the result. This result is called the net ionic reaction. So the net ionic is what I have left. I've got this, this, and this precipitate. So I'm going to put in here 2I minus aqueous plus PB2 plus aqueous yields PBI2 solid, right? The actual stuff that's happening in this reaction is the formation of lead to iodides precipitate. And so here the net ionic is showing the change that's happening, showing just a change. Okay, just the species that change. And honestly, you could also just say, okay, well, we can just put together the ions that make this precipitate, and all of the rest of the ions are just hanging out. They're just spectating. All right, so let's do a couple more examples. So one example from the homework worksheet. You can take a look here. You can have a special preview of your homework. So if we take a look, let me